Welcome to Brain Vision.
A piston cylinder contains a given mass of water at a given state. The piston initially rests on some stops, with the top surface open to the atmosphere with atmospheric pressure P0. We also know the water pressure required to lift the piston, and we wish to calculate the heat transfer in this process. So if we take the control volume as the water, we have a control mass, which from the continuity equation shows that M2 is equal to M1, which is simply M. So the mass of the water is constant. The energy equation can be written as M into U2 minus U1 is equal to the heat transfer Q plus the work done W. So let's write down our information at each state. At state 1, at 20 degrees Celsius, we have that the specific volume V1 is equal to the total volume V over the total mass M. And that's 0.1 divided by 1, which is 0.1 cubic meters per kg. The quality X is equal to 0.1, again from our tables, minus 0.001002 divided by 57.789. And so we get the quality in state 1, X1, to be 0.001713. The internal energy of state 1 is U1. And again, now that we have the quality, we can calculate this to be 83.94 plus 0.001713 multiplied by 2318.98. And so we get the internal energy of state 1 to be 87.92 kilojoules per kg. So to find state 2, we can find first check on state 1A, where the pressure is now 400 kilopascals and the volume remains constant at 0.1 cubic meters per kg. So since the specific volume is between the fluid and the gaseous volume, specific volume, we have state 2 is a saturated vapor. So and the saturated vapor is at 400 kilopascals. So V2 is equal to the vapor pressure Vg, and that's 0.4625 cubic meters per kg. The total volume V2 is equal to the mass times the specific volume little v2, and this is again 0.4625 cubic meters. And the internal energy U2 is equal to the vapor internal energy Ug, 2553.6 kilojoules per kg. Now the pressure is constant as the volume increases beyond the initial volume. So we have boundary work being done. The work W from state 1 to state 2 is the integral over the two states of PdV, which is the constant pressure P times the change in volume V2 minus V1. So this is equal to the lift pressure to lift the piston times the change in volume V2 minus V1. And we can put our values into this to find the work. So this is the lift pressure 400 kilopascals times the change in volume 0.4625 minus 0.1. And so we get the work done to be 145 kilojoules. Now we can put the work back into the energy equation and rearrange to solve for the heat transfer. So the heat transfer Q is equal to M into U2 minus U1 plus W. And this is 1 into 2553.6 minus 87.92 plus 145, which gives us our final heat transfer for this process of 2610.7 kilojoules.